Hello everyone. In the previous videos, we had gone through the definition of a random variable and we had seen a few examples of the random variables. Now, let's explore the topic more and let's see what we can do with these random variables. So, here in this video, we will go through something called as a cumulative distribution function of a random variable. So, what is this cumulative distribution function? Or you can say the CDF in an abbreviated way. So cumulative distribution function is a function which will define the probabilities for a random variable, and it maps from the real number line. So this is the domain of the cumulative distribution function. This is the CDF. You can denote it as capital F of x. So this is a cumulative distribution function for the random variable x, and its domain is the real number line, and its range is the interval 0 to 1. So you can see that its range is same as that of probability measures range. Now, what does this mean? What does capital F of x do? So we see that the probability is assigned to the intervals of the form minus infinity to some real number x. This is a Borel set. Let's say this is a Borel set B on the real number line. So we will take a pre-image of this Borel set B, and then we will see what is the value of the probability measure of the pre-image of this Borel set, and that value would be capital F of x of small x. So this would be the CDF of the random variable x. To represent this in a visual way, we can see it here. So let's say this is our sample space omega. This is our real number line which goes from minus infinity to infinity, and we take a Borel set such that it goes from minus infinity to some real number x. So this is the Borel set. We know that there is a random variable x which exists and which maps from the sample space omega to the real number line. What we would do is, let's say this Borel set is B. So we would take a pre-image of this Borel set B, which is x inverse of B. Let's say it is a collection of some elements in the sample space omega, which is this. So this is x inverse of B, and then we will take the probability measure of this and measure what probability it corresponds to. So we know that the probability measure P will only map from 0 to 1. So this will map to some value here, and this value is f of x of small x. So as this small x changes, this value here would also change. So this is the visual representation of the cumulative distribution function. If you want to write it in a mathematical way, you can write it like this. So what was x inverse of B? X inverse B was the pre-image. If you remember, this was B, the Borel set. This is x inverse of B. So this x inverse of B was this pre-image of this Borel set B. And then when you apply the probability measure function on this set, you would get some value between 0 to 1. That value is capital F of x of x, or you can say the cumulative distribution function. You can also denote it in this form, where there are some points, some elements omega present in capital Omega, and such that x of omega, so x of some element omega, would correspond to some value in this Borel set. So you can also write it in this manner. So this is nothing but x inverse of B. Now let's see some example of cumulative distribution function in order to improve our understanding. And we would do it using visual representation so that it's easier to follow. So as you had seen in the previous example, let's say we have a coin toss experiment where we can have two outcomes of a coin toss, either heads or tails. So the sample space would be heads or tails. You can write it here. So this is the sample space. And let's define the sigma algebra as the power set of omega, which would be phi, heads, tails, and omega itself. So F is a sigma algebra on omega. Now let's assume that this is an unfair coin, and let's define the probability measure in this way. So let's say the probability measure of H is 0.6. So this means that there is a 60% probability, 60% chance of heads being the outcome for a dice roll of a coin toss. And let's say the probability of getting a tails is 0.4, and obviously probability of phi would be 0 and probability of omega would be 1. Okay, now let's define the random variable x in our case. So let's say x, we define a random variable x such that when applied to heads it gives the value 1, and when applied to tails it gives a value 0. Okay, so you can say that this is a set H. So when I apply x on it, x of H, this would give you the value 1, this would give you the value 1, and let's say when I apply this value here, x of tails, it will give you the value 0. Okay, and in the previous example we had seen that why this is a valid random variable. So x is a real valued random variable. Now let's define the cumulative distribution function of x like this. Okay, so let's start with taking a few examples. Okay, now let's say I have some value of x where x is less than 0. So for x is less than 0, we know this would be the Borel set from -infinity to x. And this, if you try to take a pre-image of this Borel set, in this case it would point to nothing. So this is nothing but a null set. And we know that the probability measure on a null set would be 0. Hence the value of f of x, capital F of x, which is the CDF of x, would be 0 for all x less than zeros. Now let's take another case. Let's take a case where x is equal to 0. So in this case, for or let's say, let's define it in a better way. 0 less than equal to x less than 1. Let's define it in this way. So let's take a value x where x lies between 0 to 1 and there is an open interval at 1. So this is a Borel set B, and we know that 0 lies in this Borel set. So we know that if I take a pre-image of this Borel set, it would point to tails. Okay, and we know that the probability measure of getting a tails is 0.4. So you can say that this value would be 0.4. Now let's take the third case where x is greater than 1. So the Borel set would be this big. X is greater than or equal to 1. In this case, we know that both of this 0 and 1 would be present in our Borel set. Hence, we would know if you take a pre-image of such a Borel set, it would contain both heads and tails. And if we take the probability measure of this, P of heads comma tails, it would point to 1, as P of omega is 1. So we can denote it like this. So here we have successfully created and we have seen this example of a cumulative distribution function. If you want to map it, you can map it like this. So this is a cumulative distribution function of x. So for x less than 0, its value is 0, all zeros. When x becomes 0, its value jumps to 0.4. And this value will go till x is 1. After that, it will jump to the value 1. Hence, you can say that this is a cumulative distribution function for a random variable x defined in the above manner, where if heads is the outcome of a coin toss, then the value of our random variable is 1, and if tails is the outcome of a coin toss, the value of our random variable is 0, and it is an unfair coin. So you can say this is f of x, and this is small x. I hope you like this video. Thank you for watching.